All right, we're at section 30.2, Motional EMF. And let's share the uh, PowerPoint. Okay, what we have, you remember the magnetic field, as you see in here, the magnetic field is going into the screen. You see the little X's going into the screen. So in steady state, the electric and magnetic forces on an electron in the conductor are balanced. Due to the magnetic force on electrons, the ends of the conductor become oppositely charged, which establishes an electric field in the conductor. Okay, let's see why. You see, there's this conductor, this bar, and uh, you see the velocity is going in to the to the right there. So let's do our right hand rule. The um, the magnetic field is going into the screen. The velocity is to the right. So the positive particles, positive to the palm, they go up, and the negative particles go down. So let's see what happens as this conductor goes. You see the positive charges go to the top, and the negative charges go to the bottom, and that sets up an electric field um, in the conductor. So we see that the sum of the forces equals zero, and then you've got forces coming from um, two directions. You've got the QE, the fact that you have the charge and electric field, um, and you have the charge from the velocity uh, in the B field, and those equal zero. So E equals to VB, the velocity times the magnetic field. So delta V is equal to the E times L equals BLV. Um, Now here's a case, and this is actually a question in the handout on the Thursday's lab. You can see that um, we have uh, a moving bar on some rails. A counterclockwise current I is induced in the loop. The magnetic force FB on the bar carrying this current opposes the motion. So you have the F applied, but you have a FB going in the opposite direction. So the flux, the magnetic flux is uh, BA cosine theta. Well, here the cosine theta is 1, and the area is L, the length. You see the length over here along the resistor L. The area is LX, and here's the X over here. So the phi is equal to B times the area. So the induced current, it comes from the induced EMF, which is, remember, E is equal to the minus d phi dt, which is equal to minus ddt of BLX. Well, what is dx dt? You have BLX, d of ddt of BLX. Let's take dx dt. That's equal to the velocity. So uh, the induced EMF uh, is equal to minus BLV times the velocity. Um, okay, and so the current is equal to the induced EMF divided by R. You can see the R is here in the circuit, is equal to BLV over R. I jumped the gun there. Okay, so E is equal to BLV. We combined the two figures from the previous, the uh, the electric field in the conductor, and this one of the sliding conductor on the rails. We're applying the work, um, the sum of the work applied, that's applying the force, and the transfer by electrical transmission, that's the ET, they have to be equal to 0. So we had that long equation in previous chapters. So here we have work applied, and we have just the transfer from electrical uh, transmission. So the ddt of the work applied is equal to minus d, dt of the transmission or the transfer by electric transmission. So that's the power applied equals the negative of the electric power produced. And so power applied is the F applied times the velocity equals FB times the velocity, and that equals to ILB times V equals IBLV. So in one case we have I times the EMF equals I times IR equals I squared R equals the power, the electric power, the minus P from the minus P from the electricity. Okay, now it's like, well, when are we ever going to see this? We'll see some problem examples. We're going to have the wing of a plane going through the Earth's magnetic field, but here was a real application. This is back in 1990, in the 90s. This was called the Tether project. At least that's what I knew it by at Southwest Research. If you look on the left, this is an artist's conception. You can see there's a space shuttle down at the bottom of the photo drawing, and there you can barely see it. You probably can't see it on the screen, but there is a fine tether wire hooked to this satellite, and the idea was to let this tether out, and we're talking about kilometers. We're talking 20 kilometers. That's 12.5 miles. Let this satellite go out on this long cable, and as the cable goes through Earth's magnetic field, let it induce a current to power some of the experiments. So the idea was to let the shuttle drag the tether across the Earth's magnetic field, producing one part of a dynamo circuit. The return current from the shuttle to the payload would follow in the Earth's ionosphere, which also conducted electricity, even though not as well as the wire. And the purpose was to produce electric power, generating current to run equipment aboard the space shuttle. The first attempt at the tether experiment ended prematurely, basically because the tether got stuck. It only released the satellite so far. You can see in this the right-hand photograph. You can see the tether is just going out a little bit, and it got stuck. They weren't able to do it. They did a second attempt in February of 1996, and the tether unrolled, and it went up and up. I don't know how far it got, but it was deploying. It was going up, and all of a sudden the tether broke. And after a lot of investigation, they learned that the electric current that had produced it, because of failures in some of the insulation, the electric current actually melted the tether, and that's why it failed. So the current was enough to melt the cable. Anyway, this is you can look up NASA space tether experiment, and you can read about it. It's an interesting interesting project. I knew about it because some of our people at Southwest Research worked on it. In fact, I think Dave Winningham was one of the ones that thought of the idea. He was a fellow out there at Southwest Research. Okay, let's see. All right. We have in a figure a given applied force of magnitude F results in a constant speed V and a power input P. Imagine that the force is increased so that the constant speed of the bar is doubled, 2V. Under these conditions, what are the new force and new power input? Um, well, the force, it's twice the velocity, so the force is doubled. But if you remember, the power is I squared R. So if it's I squared, it should be four times uh, the power. Let's see if my thinking is correct. 2F and 4P. The force on the wire is of magnitude FB equals ILB, and I is given by BLVR. And let's see, because P is equal to force V, the doubling of the force and the speed results in the power being four times as large. Well, they don't use the same reasoning as I do, but the answer is correct. And we'll stop there, and then we'll go on to Lenz's law in the next section.